Hello, and welcome to the Data Science Institute's virtual seminar series. My name is Dr. Leno da Silva, and I'm a data science ambassador at the Lawrence Livermore National Laboratory. Data science is essential to many of the lab's key program areas. With the help of some of the world's most advanced supercomputers, we work in a variety of fields and application domains. Through basic and applied research, our data scientists are working to solve some of the world's most pressing challenges, in areas ranging from precision medicine and advanced manufacturing to energy and national security. Here at the lab, the Data Science Institute acts as a hub for data science activities, including this seminar series and other events to introduce new ideas and encourage collaboration. Speakers from other institutions are invited to share their innovative approaches with our data science community. With recordings of these seminars, like the one you are about to watch, we are reaching a wider audience than ever before. So, welcome. If you have questions or want to follow up after the presentation, check us out online at data-science.llnl.gov or send us an email at dsi-seminars@llnl.gov. Now, sit back, relax, and enjoy the seminar.
People would like to do. You have X-ray diffraction patterns, which are in a reciprocal space. So, and you want to extract that information and integrate with some of the existing tools. And you have some other kind of acoustic or some other sensors which have some like a different information on your actual process. And at the one of the end goal is usually predictive analytics that people want to do and find out variability and complexity of these processes. So I'll just take an example of synchrotrons. So we collaborate a lot with synchrotron facilities and get a lot of data from them. So in general, if you look at these different facilities across the world, so there are a lot of synchrotrons from since 1990s. They produce like massive amount of data. And so vast amount of this data is never analyzed. So one of the testimony from the users is like they get say like a week or 10 days of beam time that they spend there. They write a proposal in advance, like it takes almost a year or something. And I mean, this is an expensive time that they buy. And then once they come back from there, so they usually are handed out a hard drive with 8 to 10 terabyte of data, and which they will never analyze, just like a little chunk, which may be like a few gigs or something. And that's where they focus on, and they write paper, and they're happy about that. And then a lot of resources and valuable insights they're lost because any inability to fully utilize the data, that means we are potentially like these breakthroughs are lost. So we collaborate with APS. So APS, after APS upgrade, they have data generation capability, which were earlier 1 to 2 terabytes per week, and which was when they compress it to it's almost 8 to 10 terabytes per week. So it was just on a single beamline, and they have over 70 beamlines, and they have over 6,000, more than 6,000 or 7,000 per experiments per year that they do. And production rates after upgrade, they expect to have like 500 terabyte per week. And last week I was at a workshop at CMU, and then they mentioned about like a sophisticated beamline they are building upon, and they have just 250 terabytes per day data generation capabilities. So the scale and amount of this massive data is really big. So with this, like they achieve a higher spatial and temporal resolution with all this rapid data acquisition. And they have these multimodal data varieties, like in terms of images, spectra, metadata. And so they have been around from like 1994, if just talk about APS, but they have like paid less attention to data analysis because this was never combined with the acquisition. And this is happening not just with the synchrotron facilities, rather like some other across like other materials engineering facilities in terms of whether it's advanced manufacturing or some other process going on. So we are generating a lot of data nowadays. So we are collaborating with other synchrotrons too, like Nanoterasu at Japan and TSRC. and they all have this similar scale of data being generated from all these different synchrotron facilities. So what are the challenges with these current data handling practices? As I mentioned, they spend 1 or 2 weeks of the beam time and they leave with a hard drive. So these results are incorporated into a research paper later on after a year or two. But why they don't create, why there is not a mention of knowledge graph, which is available for future analysis. Like you have all the data recorded with like a proper annotation mechanism or framework, and that could be connected to a knowledge graph. So there we can infer more information from there. So the current practice is like kind of unfeasible. So on these personal or institutional systems, as they have these large data volumes. So people have started thinking of integrating high performance computing infrastructure. But then again, there are some issues with that. So usually all these big facilities like Chess or APS or Slack, they all have their HPCs, which are integrated somehow with their synchrotrons to achieve this real-time data processing and analysis. But then there are several challenges because these data sets are vast and complex and diverse. So we need ensuring like effective storage, access of both data and metadata. So usually metadata is not recorded in a very efficient way. So most of the time when people do analysis, especially like when they originally they didn't do the experiment, a lot of time is just spent on figuring out like the metadata. So people have inconsistent way of metadata recording and the variability in the way this is recorded across different experiments and beamlines. So there is a lack of standardized metadata, and even different beamlines with the even in different experiments, they are not consistent. So they use different names for similar variables. For example, you have a beam energy, so that may be recorded as by some user as beam energy or energy beam or e-beam or whatever name like they like to do at that particular time. So we need definitely automated analysis pipelines and workflows, which is the requirement of the time. So and the bottleneck is because of this complexity in data and metadata. But most experiments, they require real-time data processing to make data-driven decisions during experiment. Even like sometimes people stop, like whenever they have the experiment is running, they give some pause and go back and analyze a little chunk of their data and come back and see, okay, we need to modify these parameters to effectively do this experiment. So those things are usually happen at these facilities, and those are very common. So definitely leveraging AI or data science, we can handle these big data. So one of the interesting concepts is from using knowledge graphs and AI reasoning. So, but then that also depend, like if you have a data which is utilizing fair standards, which are, I'll introduce them later. So that means you make your data findable, accessible, interoperable, reusable. There is a lot of buzz going on this part from like last decade. So with AI reasoning, you can do automated inference of new knowledge from this existing data, and you can enhance data query capabilities. You can discover hidden relationships and patterns, and you can also do better data integration and interoperability. So these are the things that probably we can do. So I'll give you an example from one of the experiments that was conducted at APS 1ID. So people spend almost 10 days here. And the way the metadata is recorded is, you can see they have all these over like 200 metadata variables here. And a user really doesn't know like which are these column headers or variables are used to them when they really want to analyze. And specific people which are at the beamline, they kind of know, okay, so you might be needing the 5th parameter to analyze this particular value. So and they have an inconsistent file naming convention. So what we actually need for good analysis is we need a complete raw data and complete calibration data with proper annotated metadata. But what you usually get is like this. So where, I mean, it depends on like how like that particular user wanted to name these variables. So what I can guess, so for example, this is well number 28, which is at room temperature with P20. So you cannot infer like what they really mean to say. So unless you were part of that experiment, or you have like a proper annotated recorded metadata. So you have a data acquisition rate, which is 6,000 hertz, and the metadata acquisition rate is 1 hertz. So you see all this metadata is not very well connected to the actual data. So it's not like people are not trying to find out the solutions. There are different communities like photon and neutron science committees across, I think, Europe, like ESRF and DSI in Germany. So they are all meeting time to time and discussing about like what could be the possible solutions. And so they have all this data management plan. So DMP, even in DOE proposals, you'll see like you have to submit a data management plan. And then they have like tools like to record this metadata, like a DMP tool, roadmap, and there are so many things that are available, and they help up to some extent, but they are not up to the extent where you can resolve these naming conventions across these facilities and leverage these AI tools at a scale. So so that is one of the challenge, and in just like one community. But if you so we have data sets from almost other like all the other like material science domains, like advanced manufacturing, laser powder bed fusion, directing, right, and so many other so everywhere I think this problem is kind of omnipresent. So so how AI and this knowledge representation can help in that. So like ontologies, they are kind of now like a buzzword when people talk about interoperability and semantic reasoning. So I'll touch a little bit upon them. So these ontologies can help in AI-driven automated analysis. So, but they also need like a connection to semantic web. So these ontologies usually provide a structured framework to standardize metadata and variable names. So you can get consistent definitions and relationships among these different terms of the experiments, so that you have like a better improved data integration from different diverse sources, and you can enable efficient merging and comparison of data sets. So this enhances overall quality of these AI models. And once you have this enhanced AI and ML performance, you can have this consistent and well-defined data that improves the training process of these models and reduce processing times and minimize errors. So if you look at one of our major effort is developing these domain ontologies for different domains. So we call our framework as mds-onto. So I'll talk about that later on. But this has so different domains of data. Like so in MDS characterization, you can get the ontologies which are specific to X-ray experiment, which is whether it's X-ray computer tomography or it's X-ray diffraction or some other X-ray technique. And then there are like MDS manufact, which is consisting ontologies for say different advanced manufacturing processes like laser powder bed fusion or some other other advanced manufacturing techniques. So once we develop these domain ontologies, so they are linked to this low-level ontology. That's what we call as our mds-onto. So which is connected to mid-level ontology, which is PMDCO. So that's a like a platform where you can find these terms, entities, and relationships, the proper definitions, and which is further connected to a top-level ontology, which is called Basic Formal Ontology (BFO), which is an ISO standard nowadays. And this is all connected through this schema.org to the semantic web. So that way, this everything is connected from like bottom to top, and you have a consistent way of developing these ontologies. So what the vision here is, we have developed a bilingual package in R and Python both. It's called Fair Materials. I provide the link later on in other slides. So yeah, once you have this data and you run, so you get, the user can find out like if they have uh, there exists like an existing ontology in that domain or not. If not, you can uh, describe your own words, and that can also be mapped to the existing terms. And then if not, then they can be the new words that can be added to these packages. So once you have this analysis, and then this is all connected to this schema.org, and all this ontologies, they are connected to a knowledge base. And in that knowledge base, you have the regions from your analysis. So that way you can do this reasoning, and that way it will help out to do this AI based semantic reasoning. So as I explained earlier, the way this data is handled in traditional science is really broken. So I was mentioning about like you perform an experiment with a tool, with a recipe, and you do an experiment for that a particular recipe. You generate data, do data analysis, write your results, and publish a paper. So that's like the traditional way scientists perform his experiment. But once you have I mean, there is definitely a challenge of reproducibility based on like your metadata and the way you have performed this data analysis. So once you shift to a data-driven culture, so you first will talk about this data governance, which set policies and guidelines and decision in the entire data system. And once you have those policies, you can talk about this data stewardship, which is implementation on the data governance in all like throughout the data cycle. So you have a research question, and you have a tool that you want to do, and then you have like a fair tool which kind of verify your data with the recipe for your experiment, and then you have an ontology for that particular recipe. And once you have that experiment data and the analysis, so you again have an ontology at each of these stage. So once you develop the pipelines or like the analysis pipelines, it will again have some ontological connections. So that way everything is well connected through this ontological framework. And so the time to science is like reduced, and you can you can generate better curated data sets, packages, and papers, everything. So this is like a advantage of like a data-driven culture where research around this data quality complements this structured framework. So that is one thing. And so this all starts with the data governance. So where you have a proper way of data security, metadata management, data quality, storage, and everything. So to ensure that data is used efficiently, and it helps to keep data like available and all this fair standards. So this is the MDS cube data life cycle that I was mentioning. So we receive data from these NNSA labs, including Livermore and all these three NNSA labs and other places. So we ingest data in our system called Cradle and develop ontologies which make like help making data interoperable. So that's like one of the requirement of this pair principles, and do data analysis and modeling. And then all this knowledge from data models is stored and used to build a knowledge base, so which is more efficient and reliable analytics you can do on top of that. So so I didn't go much into the like ontology here, but you can see from this illustration, which is like defining concepts, terms, and relationships, which are important to standardize a way to represent knowledge. So if you have like just a data here and you add information and that connect it, it becomes knowledge. So similarly, you have say data, which is locations of different cities and labs and everything. And then what are the connections between these nodes? So this kind of ontology can be applied to create knowledge graphs, which help in semantic reasoning. So that is the way the new knowledge has been created. So when we talk about knowledge graphs, so you have like an ontological framework which defines relationships between different entities and nodes, and you have data on top of that, so that allow linking. And so we can use this semantic schema and semantic metadata to describe this. So that way, when you create a knowledge graphs, so it will allow inferences here. So we have like just given an example here. For example, USA like has a subregion called California, which has a subregion of Livermore, which is so LNNL is located in that, which is also part of NNSA. So that funds LNNL, which funds MDS Cube that we are, and we fund students. So that's how like everything is connected. And now you can ask different questions based on this ontological framework with actual data on that. So through these inferences, this knowledge graph can provide additional information that is not explicitly stated. So you can have like this, you can infer new relationships among them. So for example, like you have like these two distinct nodes, and there's a connection between them. So that knowledge can also be inferred from this kind of framework. So if I talk about the current status of materials domain ontologies, so there are 40 plus material science domain ontologies that currently exist. So they cover different domains ranging from battery interface to nanoparticles. So some of them are listed on the portal called Math Portal. And so, but there is no guidelines for creating ontologies in materials and data science space. So which is leading to heterogeneous and non-interoperable ontologies. So that's why it's important to map them to like a top level ontology. So this is well defined in like a medical community. So they have a portal called bioportal, where you can find like more consistent domain ontologies, because they are kind of engaged in that work from the past few decades. So and in material science, I think there are not much domain ontologies have been developed so far. So it still needs like there is like lack of significant efforts in that space. So if I talk about the framework that we have developed, so this has a website called Find the Docs. You can get information about our package and our ontological framework. So the link is given in this doc if you want to take a picture or something. So we have just released 0.6 version of that, so which is again connected to PMDCO, which has over 30 domains in materials and data science. And these domain ontologies created through this framework from the basis of MDS ontologies. This has over 62,000 triples. So that been like all this nodes, they have the like information about their properties. So this is the link for the Fair Materials Find the Docs website, where you can find this all OWL and JSON-only files, and there are detailed documentation if you want to check it out. And they have also hosted the ontology visualization tool called WebOwl, and JSON-only visualization tool is JSON-only playground. So you can look at your ontological framework and the schema, and you can play with that. So you can test that out. So this is all about the package information. So once you run this package, it serializes the RDF lib graphs into an OWL and JSON-LD format. So you get these 4 kind of outputs. Once you map your, so for example, you have run an experiment and you have some variable names which may be existing in an existing ontology, or it may have like new variables. So you can just map them through like Google Sheets, and you get like a visualization in terms of a PNG, an OWL file, which you can open in WebOwl or somewhere, some other ontology visualization tool, and you have a JSON-LD file with the ontology schema and populated ontology data, and then you have a documentation in HTML file. So that's what you can get from that. So this is stuff I have already talked about. So once you have defined this ontological framework and knowledge graph, so how we can do the like data science and like developing models, those kind. So I'm just giving like a snapshot on the platform that we are using. So we use a Open on demand to do data science. So we have all this integrated development environment that are hosted here. this is web-based access to HPC. So this is pre-configured data science environment. So we have access to data science notebooks and IDEs and other diagnostic tools, so that we can see here. And this is more information on our computing cluster, so which has like a 2.6 petabyte of distributed computing storage, and this on-demand containerized apps with this cloud data platform. So this platform is able to train hundreds of deep learning models. So we have like 2 papers on this platform. If someone wants to read more about this platform, I can just share that information later on. So I'll just give you an example like how this is efficient than traditional HPC. So in HPC, like all this is a scale-up computing where you can say begin from a little small script and you generate a lot of simulated data. On the other hand, this the platform that we have built up is Hadoop-based distributed computing environments, which has Hadoop for petabyte scale data. It has Impala, which performs SQL-like queries, and Spark, which is for in-memory distributed computing, and NVIDIA Rapids, which is used for distributed GPU training. And with this new data format, so some of the performances that we have compared here. So if on HPC, if you want to construct like a 100K adjacency matrix graph, so it usually takes 19 days on traditional HPCs with 24 CPUs, which reduced down to 19.1 minutes on this Spark or Hadoop-based system. Similarly, image conversion, we just have 10,000 images, which you have to convert from BW format to TIFF. It takes 11 hours on HPC, and we reduce down it to 0.62 hours. And if I talk about image deep learning, so we train several these image segmentation deep learning based models. So if training 240 deep learning unit segmentation model take 5.1 days on HPC, which is reduced to 5.2 hours using proper management of these steady freaks. So we have done some other benchmarking too on our platform, so which is available in these 2 publications. I think it's just one here, but we have a recently publication on this as well. So this is all about platform, but now I'll talk about actual feature extraction and how we have done this analysis. So the work was conducted by our grad student called Tommy Chiardi. So in this work, so we have this verification framework that I have just discussed before, and then we have run a feature extraction pipeline where we leverage deep learning for automated feature segmentation. And then we do statistical quantification of these detected features for attribute extraction. And once we have those features, we can do the graph summarizations here, which you can create spatiotemporal constructions for these compact representations. And once you have these graph summarizations, you can do scene graph constructions where you have all these features embedded in those temporal insights. So you can look at a specific behavior over time, like how a crack is propagating or something like that. And once you have all this representation, you can train graph neural networks, which are inferential, predictive, and generative models to extract to get more insights on that. So this was a sample which was collected from a decommissioned Navy ship, which was in in 30 years old. I think 30 years in actual field, and then later on it was decommissioned. So there were aluminum magnesium alloys, which plates which were extracted from that sample, and it was tested at Diamond Light Source at UK. So, and then if you see at this particular XCT image, there are thousands of features per 2D cross section, which includes different fractures, inclusions, or pores. So once we do image processing for these weak supervision annotations, so which can extract this fracture information, inclusions, and later on we train it. Once we have these extracted features from traditional image processing, we can use those features as labels for our deep learning model. So here we trained a unit model, which is turns out to be a robust feature extraction mechanism. And once we have these extracted features, we can reconstruct them in 3D. So we can again map them and reconstruct them, and then we can look at their special or temporal characteristics. So these are the 3D reconstructions of those features. So here you have like 250 slices of that XCT characterization, and you can see the fracture and inclusion reconstructions for 250 and 50 slices respectively. And if we talk about the statistical characterizations, so you can see this exact sample level insights. So we have like a count number of over 161,000 inclusions. So you get information up to a voxel level. So and with all the geometric characteristic of these features, with this average major axis and their volume and volume fraction. So in terms of a special features, you can ask questions like how many inclusions exist in 1 millimeter cube. And for the temporal features, you can get like, say, what is the average fractional length over time? So these kind of questions you can ask from this particular pipeline. And then we also have information at defect level granularity. So where you can query X feature that matches a set of attributes for these thousands features detected. So I'm showing here one of the largest inclusion at a time step 225 and their attributes. So it has a measure axis around 43.1 and its volume in like voxels at 1340. So this is automated extraction of over like 10 million total features throughout this 4D XCT dataset. So this is one of the demonstration where we have extracted the different features. And once we have these extracted features, so we can use graphs for further analysis. So, and these graphs will provide flexible representations that are capturing spatial and temporal information efficiently. So, which is not usually available when you kind of represent your features in a tabular data. So this is analogous to neural graphics primitives where you have these positions and all the other parameters. So you can get information, their attributes like color, density, and sign distance. So in this particular experiment, we have these single 3D XCT voxel representations where you have this image size and then over 2,000 slices. So that way you can get this 13.2 billion data points. And once you have this 3D graph representations, so it can reduce down to around 2 million data points. So once you have these graphical representations, you can generate these summary graphs where you can translate 3D feature stacks and attributes into graphs. So with their characteristics like their major axis, volume, or orientation. So all these fracture, they are embedded as a node here with all these features. And once you have all these nodes set up, so in graphs, they can get information from their surroundings, and you can train like a graph neural network model. So this is the ongoing work. So we have done this feature extraction and like scene graph representation, but then we still need to train graph neural networks further to leverage more to get more insights. So this was a like slow strain test, so you can see at 3 different timestamps like what are the behavior of these different defects over time. So now once you have created like this spatiotemporal scene graph generation, you can ask different questions when you say label these actions and relationships to identify what is occurring both spatially and temporally. So this like whole thing first enables the like to it provides like ability to translate this terabytes of experimental data into interpretable science, and then later on we can ask questions like whether a crack will propagate in a certain direction or whether like 2 different cracks they have some effects on each other. So those kind of questions could be further revealed here. So and in graphs, if you can see, it can do tasks at different levels, like you can do node level or edge level tasks. So you can do operations like node regression, where you can ask how much will a fracture grow in the next time step, or you can do a link prediction where you can ask whether any precipitates will have like a preference where the fracture will go over, or it has like a graph explainability level questions where which defects are most influenced and displacement. So those are the things that probably you can ask from these kind of models. And so this is going towards this concept of data-driven digital twin, where we learn from this kind of data representation and ask more questions. So another thing I wanted to show is about a platform called Cradle Data Explorer, where once we have all these different kind of multimodal feature extraction or multimodal learning, we can just to visualize their performance over time. So I have a little video here, which is from a different data set and problem, but it will just demonstrate how does it work. Oops. So once I request a node and I can open this Cradle Data Explorer. So here we have this geospatial data set of on a certain geometric region, and you can just map. You can visualize that in real time. So there is a crop prediction. So first we have different temporal and spatial data sets here, and we have done this data integration and then prediction on whether what will be the corn growth or soybean growth in a particular region. So you can just visualize using this platform. So similarly, we have this platform available for looking at visualizing this feature extraction pipeline for XCT, XRD, or some other project that we want to do. Right. So yeah, so as I introduced, these graphs are super useful, and since I have only 15 minutes, so I'll just touch upon data-driven digital twins, which I wanted to talk about after this feature extraction. So foundation models, they are very much in use nowadays because they can be trained on just without any annotations. You don't need any labels to train them, and once they have some self-supervised learning way, and once they are trained enough, you can have a little fine tuning, and you can do different types of tasks. So when it has learned, it has a compact representation of the information in your data. So you can have a variety of tasks that you can do on those foundation models. So here we propose graph foundation models, so that I will talk about. So before that, digital twin, people are using a lot in different manufacturing facilities, because it's a kind of a digital model which of a physical product, system, or process. So they provide they emulate the behavior of the physical system as virtual system, and it do information exchange between the real and virtual space using different sensors and other ways. So this has a history, it was alluded to in a book in the 90s and appeared in a University of Michigan talk in 2003. It appeared in a 2010 NASA report where it improved the physical model simulation of spacecraft. So, I mean, this is useful, and so often it is assumed to be there are digital artifacts that accumulate during product development, and so all this linked data that is generated during produce is often used to be assumed to be a simulation physics calculation of the systems. So in general, this data-driven digital twin that we are proposing, it has data and it has a digital representation of the product, but it is learning from the large data streams rather simulating the actual model. So that's a different perspective that we are putting forward. So this will do task specific machine learning, where we have, say, generalized LLMs versus these scientific foundation models. So I'm using here some slides from Henry Kaman's IBM talk. He mentioned about the concept of these foundation models. So where if you look at these classical AI models, so they are trained on specific tasks. So you have a database, you want to predict certain property or like certain behavior from that. So you can do a regression, classification, or data imputation, or a reconstruction. So there can be a variety of ways you can train different deep learning or machine learning models. So those are classical AI models, and they are purpose-built and siloed. But in foundation models, you have a one base supports, which is supporting multiple tasks. So as I mentioned, so these foundation models, they are trained a lot of data, and once you have, they are trained enough, so they can be tasked to do like variety of things. Like you can ask questions about classification, imputation, reconstruction, whatever you want. So that is one of the advantages you have. So they usually have like a pre-trained encoder, which is learning the compact representation in your data. So, and it can learn from any kind of data. So for example, it has image data on EL, electroluminescence, photoluminescence, satellite, drone, or whatever. And then it uses a CNN encoder with image masking for validation. And so it can be used across diverse multimodal data sets for pre-processing, and then it writes to graphs. So you have node and edge feature vectors, and then we can use this graph encoders. So once you have like this pre-training from a particular data source, so you can leverage that for doing different tasks. Like you have a reconstruction here. So these are all satellite imagery data sets where once your encoder has learned like a compact representation of these images, so then this decoder can be employed to do this reconstruction here. So now once your this model is trained, so you can do like task specific labeling. So if you want to perform like a different task with their hyperparameters, and now you can replace the output layers with the one that you are interested in, and that way you can fine tune. And now you have this trained like scientific domain foundation models. It could be used for inference, prediction, and it has like an increased efficiency if you compare it to the traditional models. So this is kind of the idea where we started on, and then we translated this to these three different examples in three domains. So we have this PV power plant datasets from SunSmart schools that were employed in Florida. And then another dataset was on laser powder bed fusion, where we printed several single tracks. So these were like 446 tracks that we had. And then we have some data on the in situ and ex situ characterization. So where we wanted to know like their part quality. So, and then there are like several defects like pores or something that those were present. So we wanted to ask different questions on that. And then we have this DIW direct ink writing data, where you want to do some error estimation. So here again, we use the similar approach. We have these different data sources, and we first run a data verification pipeline where you can verify your data, and then it can feed into a graph encoder where it learns the compact representation of your data. And once you have like a learned encoder, so you can further fine tune with like a different parameters and like this task specific supervised learning. And now you can ask different questions in terms of inductive inference, whether you want to forecast the performance of your PV power plant, or you want to know about any anomaly that happened during the production process, or you want to do a reconstruction or anything else. So in this particular work, we have PV power plant data where we have this learning task as imputation and power prediction with so these are the number of nodes in that graph. So that was 90, 123, 428 in these three different tasks. And this is like a temporal aspects where we have a 2 year of PV power plant data, and we have 250 time step data on DIW, which has a physical object like 123 5-layer 3D parts. And in terms of laser powder fusion, you have 428 tracks. But so once you have these tracks, you have a radiography data on that. So we have like first a image segmentation pipeline where we segment all those tracks and then feed that information into this graph foundation model. So we use like the same architecture for all these three different tasks to just demonstrate that the concept of this foundation model is viable. So here you can see these foundation models as graphs where again this set of objects nodes that are connected by some type of relationships like edges here. So these nodes, they represent an entity like a track or some other information. So and then they exchange information with their nearby nodes. So they can be undirected or directed, whether in terms of like whether they're exchanging information with their surrounding nodes or not. So we have made this foundation model available on GitHub and also the datasets and train model on OSF as an open source here. So you can take a look at that. So in terms of PV power foundation model, so we have like these SunSmart schools that are those are like smaller PV power plants across the Florida state, and you can see this heat map of adjacency of these different nodes. So that way it is like how it is connected, and once you have these graphs connected, you can predict their performance. So first you can do this data imputation, so you can get the information wherever like there are missing data, and then you can also do the prediction here. So that is one thing we could do. And in laser powder bed fusion, we have a build plate here, which had information about these 428 tracks. So these are single tracks that were printed. This experiment was conducted here at Livermore, and so we first have like an image segmentation classifier where we wanted to know whether this particular track is complete or this is incomplete, and there is some discontinuous continuity there or not. And then we wanted to ask more complex questions like if there are any pores within the track or if there is no pore. So usually they have like certain types of defects because of processing parameters. So once you have these tracks segmented, so we segmented these tracks from the radiography images, and then we ran this integration pipeline where we integrated pyrometry data with this radiography data and extract the information about the widths here across this node. And so all of these different parts, they are connected to as nodes, and when each track is encoded as node with relevant in situ and ex situ features. And once we have these features, we can now ask questions from using these classifiers, whether the pore is complete or not, and whether like the track is complete or not, and whether there are some pores or not pores. So that way we can ask these questions using this graph foundation models. So this is the second task we have accomplished, and then in the third task we have this direct ink-write pattern transfer. So we have like a set of simulation set of like printing parameters, which gives you information on the print direction in X, Y, and Z axis, and then there is a like a error associated with that actual printing versus the actual with the G code that have been provided. So you can again make so one particular DIW mechatronics layer, you can represent them as node, and all these nodes are then connected together, and once you have this kind of model, you can predict the like any error which was associated with the printing part. So these are the three tasks that we have accomplished using these graph foundation models, and it was I think well done. It was kind of good enough to learn features from all these different variety of tasks. So with that, so this work was submitted in scientific reports, and still it's under review. And yeah, again, you can find the data sets and train models on our OSF page. Yeah. with that, I would like to acknowledge our MDS Cube and SDLE Research Center. And thank you for attending my talk. And if you have any questions,